Good morning, students. Let us start with numerical problems on doubly reinforced beam, that is type 2. So in the previous class, we have solved the problems on type 1. Okay, so let us see how these type 2 problems will be analyzed. Okay, the first problem is like this. A rectangular beam of dimension 230 mm and 600 mm is to carry a superimposed load of 40 kilonewton per meter over an effective span of 6 meter. Okay. Determine the tension and compression reinforcement and use M20 concrete and Fe 415 grade steel. Effective cover is 40 mm. Okay, so the beam dimension is given, that is width of beam and overall depth. It is overall depth, capital D is given. Okay, and this beam has to carry a superimposed load. Okay, so that is a live load. Okay, in the form of UDL, that is 40 kilonewton per meter over an effective span of 6 meter. So 6 meter will be the span of the beam. So now for this beam we have to determine tension and compression reinforcement, that is bottom steel, whatever steel is provided at the bottom, this is tension steel. We have to find out what is AST, area of tension steel, and top steel provided, it is compression steel, the ASC. We have to find out AST and ASC. Okay, and in turn, since load is given, okay, so we can calculate the moment. Okay, so now here this is the overall depth of the beam given, capital D is given. Okay, and it is mentioned that, okay, effective cover is 40 mm. So here also it is 40 mm, D dash is also 40 mm, and if this effective cover at the bottom steel also it is 40 mm. Okay, now if this is the capital D overall depth minus this effective cover will give small d. Okay, overall depth minus, right, this effective cover will give effective depth. So effective depth small d is equal to capital D minus effective cover 40 mm. So this comes 560 mm. So small d, that is effective depth of the beam, is 560 mm. And then this d dash is the effective cover to the compression steel. D dash is equal to 40 mm given. Okay, effective span small l is equal to 6 meter. Then FCK, that is characteristic compressive strength, M20 means it is 20 Newton per mm square, and Fy 415 Newton per mm square. Live load given 40 kilonewton per meter. Okay, right. Now first we want to calculate the moment. Okay, directly the moment is not given here. Okay, load is given, so first we'll find out the moment. So for that, total load you have to consider. So what is the total load now? In this total load, one is given live load, another we have to calculate dead load of this beam or self weight of the beam. So dead load or self weight of the beam is equal to what? You have to take gross area of the beam. Gross area means total area, that is width of beam and overall depth of the beam, that is B into capital D into whatever this reinforcement is there, concrete is there. We have to consider density of RCC. Okay, B into capital D into density of RCC. So we have to substitute in meter now. So 230 mm means 0.23 meter. Okay, then 0.6 overall depth, 600 given, 600 means 0.6 meter. Then density of RCC is, for RCC it is 25 kilonewton per meter cube. This is in kilonewton per meter cube, that's why you are substituting these two are also in meter. So 0.23, 0.6 into 25 kilonewton meter cube. So the total dead load or self weight of the beam will be 3.45 kilonewton per meter. Okay, 3.45 kilonewton per meter. And live load is given how much? 40 kilonewton per meter. Add these two. So then we're going to get the total load in the form of UDL, that is small w. So total load is equal to 40 plus 3.45, this is 43.45 kilonewton per meter. So this is working load. Okay, this is working load. If you multiply 1.5 okay, we'll get factored load or ultimate load. So WU is equal to 1.5 into this 43.45. So directly we'll get WU. Okay, so WU is equal to 65.157 kilonewton per meter. So this load, total load, will be in the form of UDL. It is in the form of UDL, which is acting over the beam. Okay, so for the first step is, okay, calculate the total load. Okay, then moment we are going to calculate. Once the load is known, moment you have to calculate. See, this is the 6 meter span. Over this there is a UDL, whatever you have calculated now, that is 65.175 kilonewton per meter. So as we know, factored moment, now this is a simply supported beam subjected to UDL. So for simply supported beam subjected to UDL throughout the span, okay, what is the maximum bending moment? Maximum bending moment at the center now. Maximum bending moment at the center of the beam is given by WL square by 8. So MU. Now if you are taking WU, you see it is MU. If you take W here, then it will be M. Okay, anyhow we have calculated WU, so directly we'll get MU. So maximum bending moment or factored moment is equal to, MU is equal to WU L square by 8. WL square by 8. Since it is simply supported with UDL, this is WL square by 8. So substitute value 65.175 WU into span is 6 meter, 6 square divided by 8. So the factored moment or maximum bending moment will be 293.3 kilonewton meter. Okay, 293.3 kilonewton meter. So therefore this is the factored moment. By knowing the load, we can calculate MU. Okay, now this is a total MU. Now moment of resistance, okay, the moment of resistance of singly reinforced beam. So without this compression steel at the top, if you consider only singly reinforced beam, then what will be the maximum moment? That is MU limit. Okay, so MU limit is equal to, now grade of steel is Fe415. So for Fe415, maximum moment of resistance MU limit is equal to 0.138 FCK BD square. Okay, 0.138 into FCK is 20 into D, B is 230 mm and D is 560 square. So this MU limit will be 199.1 kilonewton meter. Okay, so first calculate MU, then calculate MU limit depending upon the grade of steel. Now compare these two. Compare these two. So what you can get here is, so MU is more than MU limit. Okay, comparing MU and MU limit, since MU is greater than MU limit, the beam is designed as doubly reinforced beam. Okay, so remember here in this problem they are not mentioned which beam it is. It is a singly reinforced beam or doubly reinforced beam, they are not mentioned here. So that's why we are comparing these two, and after comparison we can get whether the beam is singly or doubly. Now here, if it is MU is greater than MU limit, so the beam will be designed as doubly reinforced beam. Okay, so this is the first step. Next we have to calculate area of compression steel, that is ASC, that is top reinforcement. Now again we know that total ultimate moment of resistance of doubly reinforced beam, total, okay, for this what will be the moment of resistance of this doubly reinforced beam is, total is MU. So total MU is equal to, it is divided into 2, MU1 plus MU2. Okay, total moment of resistance of doubly reinforced beam is equal to MU1. MU1 is nothing but MU limit, that is maximum moment of resistance of singly reinforced beam plus MU2. So total MU is equal to MU1 plus MU2, or MU is equal to, MU1 means MU limit plus MU2 moment of steel beam. So moment of steel, moment means force into perpendicular distance. So force is stress into area, stress FSC, area ASC. This is force into distance, that is D minus D dash. So this is force into perpendicular distance. So force is stress into area. Okay, so total mu is equal to mu limit plus FSC ASC d minus d dash. Okay, so therefore ASC is equal to this, we want no area of compression steel. So ASC is equal to this mu minus mu limit, mu minus mu limit. Okay, that is equal to divided by this FSC into d minus d dash. Okay, so ASC is equal to mu minus mu limit divided by FSC d minus d dash. But here we know mu is known, that is this mu is known, mu limit is known. Okay, d and d dash are known, but only thing FSC you have to calculate first. Okay, that is, okay, first find out the FSC. What is FSC? This is stress at the level of compression steel, FSC. Right? So since the grade of steel is what? Fe 415. Okay, Fe 415 grade of steel is given. So for this we are going to refer table F. Okay, table number F from SP16 code book. Okay, so from go to table F in SP16 code book. So from d dash by d ratio, in the first type of problems we have calculated this using the table. Same way we will going to find out this. So after referring this table F, FSC will be 353.73 Newton per mm square. This is the stress at the level of compression steel. Okay, so find out FSC from the table F SP16 code book. After calculating this FSC, substitute in this formula, that is ASC is equal to mu minus mu limit divided by FSC into d minus d dash. Okay, so mu is 293.3 kilonewton meter minus mu limit 199.1 divided by FSC 353.73 into bracket small d, that is effective depth minus effective cover d dash. Okay, so we'll get area of compression steel, that is total area at the top is 512.12 mm square. This is the area at top. So now assuming, now we have to find out the number of bars. Okay, this is the total area. How many bars we have to provide at the top? So for that we have to assume the bar diameter. So you may assume, some may assume 12 mm diameter, some may assume 16 mm diameter. Okay, some of you may assume 20 mm diameter. So it depends. Okay, so you can assume 12 mm, 10 mm, okay, 16 mm, 18 mm, like that. So let us assume 16 mm diameter bars. Okay, so for 16 mm, how many numbers you have to provide? Okay, so therefore number of bars. Okay, number of bars is equal to, how will calculate? Total area. This is the total area. Total area required divided by area of one bar. Which bar you are providing, that area. So total AST is 512.12 divided by area of one bar, pi by 4 d square. So d is here diameter. Which diameter we are assuming? 16 mm. So 5 by 4, 16 square. So this comes out 2.55. So we cannot provide a 2.55, round off to this higher value, 3 numbers. So at top we will going to provide how much? 3 numbers of 16 mm diameter bars. So that will be your compression steel. So this is finding out the compression steel. Next, area of tension steel. Okay, area of tension reinforcement, that is AST. Now this is ASC. What we are providing, 3 bars, it is ASC. Now we have to provide AST, which is provided at the bottom. So we know that again. Okay, total compressive force is equal to total tensile force for the singly reinforced beam, that is 0.36 FCK B into XU. Okay, total C. 0.36 FCK is for stress, 0.36 FCK is stress into area B into XU, that is equal to 0.87 FY AST1. Okay, singly reinforced first, AST1. 0.87 FY is the stress, area of tension steel at the bottom for singly reinforced beam is AST1. So C is equal to, or C1 is equal to T1, what you can say that. So from this we can find out AST1. So AST1 is equal to what? 0.36 FCK B into XU divided by 0.87 FY. But here the first singly reinforced we are considering at the maximum steel. So wherever XU is there we can put XU max. Okay, put XU is equal to this, XU is equal to XU max. So substitute the value. So what is XU max now? We have to calculate XU max. Now grade of steel is Fe415. So for Fe415, XU max upon D is equal to 0.48. Okay. For 415 grade steel, XU max upon D is equal to 0.48. Therefore, XU max is equal to 0.48 into D. Okay. So substitute 0.48 into effective depth 560 mm. So therefore, XU max is equal to 268.8 mm. Okay. XU max is equal to 268.8 mm. So this will be the XU max. Here substitute. Now AST1. Okay, AST1 is equal to 0.36, FCK is 20, B 230 into XU max divided by 0.87 FY. So area of steel in the singly reinforced beam, AST1 1233 mm square. This is AST1. Now next AST2 you have to calculate, because total AST is what? AST1 plus AST2. So this is AST1. Now similarly we know that in the steel beam again we have to consider 0.87 Fy AST2 now. Okay, this is again stress into area is equal to stress into area of the concrete. So 0.87 Fy AST2 is equal to Fs into ASC. So therefore AST2, we want AST2 is equal to Fs into ASC divided by 0.87 Fy. Okay, so substitute the values FSC, ASC divided by 0.87 Fy. So AST2 is 501.74. Okay, 501.74 mm square. So this is AST1, this is AST2. So find out the total area of tension reinforcement. AST is equal to AST1 plus AST2. Okay, so add these two, we'll get total AST 1735 mm square. Total area of tension steel which is provided at the bottom is 1735. Here also you can calculate number of bars. So assume the bar diameter, okay, 16 mm or 18 mm diameter. So that is total AST. This total AST divided by area of one bar, will get the number of bars. So we have calculated area of tension reinforcement, then this is area of compression reinforcement. This will be area of compression reinforcement, that is 3 bars. Here you can calculate number of bars, we are not calculated, but you can calculate also here. This is AST, this is ASC. Okay, so this is the problem which considered as a, which will be considered as a type 2 problems. Here directly moment is given, so moment we have calculated here. Load is given means moment we have calculated means it is given, like a given data. We have to find out AST and ASC. Okay, this is the second type of problem. So hope you understood this the problem. So in the next class again we'll come up with some more problems on type 2. Okay, so if you have any doubt feel free to ask. Okay, so practice this problem. Okay, so let us conclude this class, and in the next class some more problems we're going to solve on the doubly reinforced beam type 2. Okay, so thank you very much for attending this session. Thank you.